Hi everyone, welcome back to DualFUSION training module. This is training module number 2, Delamination 2. So again, this module is going to be a continuation of from module 1, and today we're going to be taking a look at delamination, but we're going to look at it from the drug container interaction. So we'll be talking about drug formulation. We're going to look at the drug container interactions, different mechanism of delamination screening, and also DualFUSION and how DualFUSION helps and eliminates this problem of delamination. So again, you've seen this table in module number 1, and again, what we're trying to see here or in module 1, where we talked about the different influencers of delamination, and we explored in details everything that has to do with the vial. So we talked about the chemical composition of type 1 porosilica glass vial, the manufacturing processes, the different coating that we can apply to the type 1 glass, and also post-manufacture treatment, deparogenation, water rinsing, and autoclaving, and how exposure to heat or water increases the risk and increases the probability of delamination. In this module, we're going to be taking a look at drugs. So we're going to be looking at drug container reaction, what are the drugs and what are the different chemicals that can affect or can increase the probability of delamination. That being said, for drug formulation, we spend a lot of time, or the main ingredient or the active ingredient takes a lot of attention, gets a lot of attention from the drug manufacturers or the drug formulation scientists. But there are other things too that need require some attention. So the diluent, the antioxidant, solubilizers, and also preservatives. So these are all different chemicals that are included in the drug formulation, and all of these can react with a container, with a primary container. In this case, we're talking about a glass vial or a DualFUSION vial. So pH, pH, really all the chemical substances or solution are characterized by really few different characteristics. One of the major one is pH. It's very important, it's very common, and a lot of solutions are characterized by their pH. And over here, if we take a look at the pH spectrum, it goes from 0 to 14. And I want to start by looking here in the middle. So in the middle is water. Okay, in water is H2O. If we break it down, is H plus and OH minus. Okay, and so this is a hydrogen ion, and this is a hydroxyl ion. And at neutral pH, the hydrogen ion is equal in concentration to the hydroxyl ion. So the concentration of H plus is equal to H minus. It's going to give you a neutral charge of 0. Now, if we go to the left side, then the material becomes more acidic. And what we mean by more acidic, we means that hydrogen concentration increases. And this is a logarithmic scale. So one jump from 6 to 5, that's a huge jump. So the scale could be deceiving, but one going from 6 to 5 takes a lot of effort, and it's a big difference. But anyway, this is more acidic. The more you go to the left, the more acidic the solution gets, which meaning the more H ions you'll have. Again, now looking at the right side, the more you go to move to the right, the more basic the solution is, the more OH ions will be there, and the less hydrogen. Okay, so this is the hydroxyl ions, this is the hydrogen ion. Now, putting everything in perspective and give you an example of commonly used acids and bases. Let's take a look at the acids first. So stomach acid is around pH 2. Lemon juice is 2.3. So when you think of acid, I want you to think of a lemon juice, I want you to think of vinegar, and I want you to think of Coca-Cola. Okay, so these are all acidic substances. Okay, Now, neutral, we talked about water, we talked about milk, we talked about blood. So blood is very neutral. And now here's a very important thing. So IV, parenteral medications or IV medications, you can see that they're going to be injected into the blood. The blood is neutral, so most of the drug that you will see, they're going to have a little bit of a neutral um, of a neutral pH. Okay. Now, if we look at the different bases that we have, you can see bleach is a base, oven cleaner, and drain cleaner. So a lot of cleaning materials will have a high pH. And I just want you to know that, okay, look, this is a high pH. If the chemical is able to clean up your oven and clean up your drain, if it's that chemically reactive, that much corrosive, I'm pretty sure anything with that pH will have a very detrimental effect on the glass vial as well. Okay, so acid, lemon juice, basic is bleach. Okay, so that's how we define basically the pH, or define the solution that we have is by its pH. Secondly, one of the common things that you'll hear uh, in drug formulation is buffers. And really, what buffer is it keeps the solution at a certain pH. So for example, let's take a look at a phosphate buffer. Here's for a phosphate buffer. Usually people use it to keep the pH around 7 and 8. And by that, what we mean is if we add more acid, in this case, 0.1 molar of hydrochloric acid, even if we add 2 mLs of 0.1 mol of hydrochloric acid, the buffer is still between 7 and 8. Okay, so it's keeping that solution at that buffer, okay, at that pH, so it's not changing that much. Now once it's a threshold, so once it reaches a certain threshold, then the pH increases tremendously. So what a lot of scientists do, if they have a chemical, that an active ingredient that is active, or that needs a specific pH around 7 or 8 or 7.5, what they do is they use phosphate buffer, so it protects the sample. For whatever reason you have introduction of hydrogen ion or depletion of hydrogen ion, it will still maintain that pH. But remember, once it reaches that threshold, it becomes a big issue, and this is why pH shift is a big deal, and we'll talk about it in more details. Okay, so we talked about buffer. Again, other ingredients that are present in drug formulation or in your on different drugs are the co-solvent, acid solubilizers, surfactant, and complexation agents. And here's an example of all of those. You don't have to name in more details. Just remember that the more stuff, or the more other ingredients we add into our drug formulation, the more they will interact with glass, and the more you're gonna get extractables and leachables. Okay. Alright, so moving on, let's talk about how these drug formulation interact with glass. So there are basically glass corrosion, or glass, or attacks on the glass happens at acidic environment and at a basic environment. And an acidic environment, the nature of that attack, or the nature of that interaction is completely different than the basic. And we'll talk about it in more details in the next slides. So let's first examine the acid or H plus glass and glass interactions. Okay, so this interactions happens by this interaction, or this reaction is going to be called ion exchange reactions, and as the name implies, exchange. So we're exchanging one thing for another. In this case, we're exchanging the hydrogen ion with a network modifier. In this case, is sodium. So briefly, This is basically the formula for glass. So this is oxygen, silicon, and metal, okay, plus hydrogen ion. So we're going to exchange the hydrogen. So the hydrogen is going to take the place of the metal, and the metal is going to come off. So right now you have the oxygen bound to hydrogen and bound to silicon, and the metal is free, okay. H3O, so the hydrogen ion, this is the same thing as hydrogen. It just this is what it looks like in water, okay. Now just to remind you and give you a visual representation. So again, this is how our type 1 glass, porcelain glass, looks like. Silicon and oxygen all over, and it's amorphous, so each ring is going to be a little bit different than the other rings, okay. So it does not have a crystalline structure, okay. So here's sodium in red, and here's our water, again oxygen, hydrogen. So here it is in solution. So this is a container and this is solution. And then what we have here is we have the sodium ion moves from the network modifier. It moves into the solution, and the hydrogen ion comes and takes its place right here. So this is where we're exchanging, okay. So two things happen. First of all, you have the leaching of sodium into the buffer or into the drug formulation, and then number two, you have the hydrogen going into the glass. And then when you do that, then your pH, your hydrogen concentration, is going to become lower. And if your hydrogen concentration is going to become lower, it's going to become more basic. And if we're changing the pH, then we will see and examine a pH shift. Okay. So this is one interaction that happens at the acidic environment. Again, at the basic environment is going to be a little bit different. So in this one, we're going to see a reaction called network hydrolysis, which basically we are breaking down the network, the silicon oxygen network itself. Okay, and this is how delamination occur, and this is how the delamination happen. So here's our type 1 glass, and as you can see, our network has these different metals that are parts of the silicon oxygen network. Okay, so we're talking about these. So boron and aluminum are going to be part of this ring, and then what's going to happen is the water molecule, which is not seen here, but basically the OH ion is going to come, it's going to attack this bond right here, and it's going to break it. And then what you're going to be end up having, if it breaks this bond and that bond and this bond, then you're going to have this whole structure coming off in itself, and this it comes off and becomes more of a delaminate. Okay, so this is one visual representation, this is another visual representation. So in the back, this is the silicon oxygen network, this is the water molecule. As you can see, this is the silicon oxygen, and then you can see that this is the oxygen right here in red. So it's gonna, the water molecule is gonna make a bond with the oxygen here, and then before you know it, they made a bond right here. So we're changing here. So this is the network hydrolysis, and this happens at high pH. Okay. So if you want to take a look at the chemical reaction, oxygen, silicon, and silicon bound to two silicon. OH is going to come here, is going to attack this bond right there. So nucleophile attack. But anyway, what's going to happen is you're going to have two byproducts: the silicon oxygen and silicon hydroxyl right here, so SiOH. Okay, and these will come off into solution. Okay, so the main point, what we're trying to say here is there are two different chemical attacks, and there are two different interactions. One of them happen at low pH, and one of them happen at high pH. The glass, any type of material that you will have, has to protect your chemical or your product at both ends, at low and high. So if we take a look at type 1 glass, it protects the formulation really in the middle pH. It's not shown here, but quartz material, it protects it at lower pH. Okay, and SiO2 coating also protect at low pH. But SiO2 coating at quartz, they're gonna have a hard time protecting the sample at the higher pH, because the OH again goes and attack this silicon oxygen network. So the idea is of more basic equal to higher risk of delamination is very well documented, and everybody knows it. I took this slide or this table to show two things. Here we have same buffer, sodium citrate, at a pH of 6.9 and a pH of 6.1. And we got vials from two suppliers, supplier X and supplier Y. And if we take a look at the percentage of vials that contain lamelles or experience glass lamination, we're going to see is 21% and 45%. But if we decrease the pH, that percentage goes down to 11% and 19%. So that shows two things. First of all, it proves the concept that higher pH causes a higher risk of delamination or higher probability of delamination. And then the other point that this table is making, that type 1 porcelain glass vials, they're going to be different from supplier to supplier. So not all vials are the same. So supplier number X is different than supplier number Y, and each of them have a different percentage or probability of experiencing delamination. So we talked about delamination, and we talked about the interaction of between drug and glass. Now the second question is, well, how do you check for delamination? How do you see if it's there or not? And basically there are USPs for it, and the two major ones is USP 1660 and 660. Now we're not going to go into too much details in this module about the mechanism and how you test it, but what I did is I have copies of these testing methods on the S drive as well. Okay. But basically we can screen for delamination in three ways. Number one is we can take a look at the particle that it peeled off or that flaked off, and then we can look at the size, morphology, and chemical composition and determine yes, it's glass or no, it's not glass. Okay, and that will give us talks about delamination, and then it gives an idea about delamination. Test mechanism number two is taking a look at the vial surface and seeing the pivots. So if it's not very smooth, that means there are going to be some of that flaking off is going to show it, and it's going to see the pivots, and you're not going to see a nice cohesive and flat surface. And the third testing mechanism is we can take a look at the solution, and then we can see the different elements that have leached into solution. So we can take a look at the amount of silicon in the solution, the amount of aluminum, the amount of boron, and the amount of sodium in here, and that will give us an idea of if the glass is going to delaminate or not, and also if the glass has delaminated already. Here's another also, this is another slide that talks about delamination, how we test for it, but one of the things that you will hear is delamination happens over time. So delamination happens after 6, sometimes years of storage. Okay, so basically what happened is you wash it, you get a clean vial, you fill it up with your drug product, and you let it sit for 6 months or even 2-3 years, and then the glass lamination is going to form. Now, of course, you cannot replicate. I mean, in order for you to replicate this in the lab, then you're gonna have to do some kind of uh, um, fast-paced study, or you're gonna have to minimize it. So you can add the solution that you add in here. You add in a very basic solution. You add in some bleach or something similar to that very basic solution, and then the lamination will occur at a much faster than the present of a regular drug product. Okay, so hopefully I was able to give you an idea of the lamination and the different interactions that happens between the drug and the container. Now we are ready to talk about DualFUSION, and basically DualFUSION is a new technology. It's a new vials that we are selling, or we will be selling, and it combines the best properties of glass with the mechanical strength and precision of plastic molding. Okay, and really, again, these vials are targeted, and the main focus of them and our market strategy is for protecting samples, especially those who are prone to cause glass delamination, and or those who are sensitive to oxidation. And we'll talk about oxidation in a different module. So DualFUSION vials, what are they made out of? So they're made out of new material. This is fusion material, and this fusion material starts out with a COP shell. So this is a plastic shell. We're starting with that, and then we're gonna fuse an SiO2 layer. So this layer is gonna be the barrier layer. This layer is gonna stop oxygen from going into the vial, and then we're gonna fuse another layer. It's called protective layer, and this layer is gonna be called organosilicate, which basically instead of SiO2 is SiOC. So we're adding a carbon and an H. So we're adding a carbon and a hydrogen. Okay. Now, if you remember from our first module, that SiO2 layer is great. Is gonna prevent a lot of extractors of leachables. But if you put any phosphate buffer or any kind of buffer, you're gonna have a lot of silicon coming off and leaching into solution. This is why we fuse this protective layer, to make sure there are no interaction, and to make sure that if the drug formulation wants to interact with a protective layer, the OH has no space in here to break these bonds. Okay, so this is the fusion materials. So again, the fusion material is combining cyclic olefin polymer shell, adding a barrier layer, and then adding another protective layer. And this is all by plasma deposition, which we will talk about in different modules. So again, so DualFUSION, that's great. Show me the data. So let's talk about low pH. So low pH. So we know that this is called ion exchange reactions. So if we look here at the porous silica type 1 glass, we can see a lot of aluminum, boron, calcium, and iron are coming out. Okay, at low concentration with DualFUSION, nothing is coming out at all. Okay. So this just shows that DualFUSION is protecting the sample from leachables and extractors of leachable at lower concentration, and you're not gonna have drug container interaction in here. Okay. Number two is as we discussed, if you have a basic at the acidic pH, you're gonna have the H leaving the solution and going into the glass matrix, and then when you do that, you're gonna have a pH shift. So in this experiment, what they did is they put WFI water and let it sit for 6 months, and then they measured the pH of the water. So with DualFUSION, it was increased marginally on the 6 month, but with a glass vial, you can see it increased significantly. It went from 5 to 6 to almost 7 here. So that's huge. So if you had a drug in here that was sensitive to pH level, and it needed 5 to 6 pH, this drug would have been gone bad by now because of that pH shift. So pH shift is pretty strong. At high pH, again, so dual fusion vials, there's no silicon that comes off. With glass vial, there's a high silicon amount of silicon that comes off. Now, if we added SiO2 coated vials like shot type 1 plus vials, this number here, this graph would have been much higher. The silicon dissolution rate, or course, would have been much higher. Okay. So in summary, if we take a look at glass, glass really get attacked in two different ways. If we talk about acidic interaction, then the hydrogen ion comes into the glass, and then the glass releases the sodium, calcium, and potassium. If we are talking about OH, so this is a basic, then the OH is going to come and is going to break the glass network, so the silicon oxygen network, and then what's going to happen is you're going to see delamination occurring, okay, and you're going to have silicon oxide, so silicon is going to be leached into the solution. So this is just putting everything in together. So basically what we're saying here, the DualFUSION protects your sample at both high and low pH and everything in between. So again, this is also another summary slide. Again, DualFUSION protect against high pH, low pH. Now this is has no breakage and precision molding, so solving the glass issues. And the next module, or the last module, we'll talk about gas permeation. So that's it for this module. Thank you very much, and I'll see you in module 4.